and there's no overshoot, right? There are no oscillations. So that's why this is, in many cases, it's very ideal to have a critically damped system. And if zeta is bigger than 1, if a zeta is bigger than 1, you would have two, again, like this is like gonna become bigger than 0, so you would have no imaginary part, but you would have two poles. One is usually small, the other one is big, right? Both of them are negative, right? But one is usually small, one is usually bigger. Both of them are real. This system, it's called overdamped. It means that, again, you're not gonna have, so this is critically damped, this is underdamped, this is undamped, and for this one, if you're trying to reach the final value, usually like you would reach that final value very, very slowly, right? So compare this critically damped and overdamped. You see that like you damp the oscillation, but you damp it a little bit too much, right? So you actually damped the transient response so much that you just like reach your final value very slowly. This is usually the case. Usually this one pole is dominant, right? So like the characteristics of the system, the dynamics of the system would just be dependent on mainly one pole. That's the dominant pole, okay? So this is the general form of second order systems, right? So you, based on the values of zeta, you can figure out how the system it's gonna behave. There's also one case that zeta is smaller than 0. We didn't discuss this. If zeta is smaller than 0, we have negative damping. It means that our system, it's gonna behave like this. It's gonna be unstable, right? We have a positive, like this is gonna be something like that. You'd have a positive exponential term. So like this is gonna become unstable or negatively damped, right? So that's something that we don't want to have, right? So all of these are basically bounded, right? But this one, this case, if zeta is less than 0, you would have an unbounded response. So this was to summarize a second order system and how it's gonna react. So that was just like a, you've seen this in ELEX 3130 as well. This was just a review. But we looked at the location of the poles for each of these systems as well. You guys remember that we didn't discuss the impact of having zeros, but if you remember previously in the same series of videos, I mentioned like how having zeros can change the time domain response of the system. Sometimes if you have a pole on the right hand plane, you would have a dip in the beginning of your response. Sometimes you might have some oscillations. Sometimes your initial response might have some deviations first, some oscillations, small oscillations first, but it wouldn't have any impact on the stability of the system. Okay. Previously we discussed the a mechanical system like this, that we would have some, let's say like we're pulling it this way, we would have some friction here, and we found the transfer function for this system. It was like this, 1 over m s squared plus b, or you can write it down as 1 over m s squared plus b over m. Okay. So let's say that we want to apply some force here and we want to reach a certain destination. Here the input is force and you want to reach a certain displacement. Okay, if the response of the system is like this, this is the reference point that you want to reach, and let's say this is like how you reach the reference. Okay, so the proportional controller, the P controller, would look at the difference between the Y, or like, let me call it X, and X reference. So it will look at the difference between X and X reference and tries to adjust the input based on that. So if this is the K controller and this is the plant, this is X ref, this is X. So this is positive, this is negative, this is error, this is U. So if you have a proportional controller, the proportional controller takes the error, which is the difference between X ref and X, and tries to adjust U based on that. The integral controller, I should have, right, this is KP. But the integral controller looks at the integral of the error. What is the integral of the error? It's this area. These are like the integral of error, right? So over time, it takes a look at the integral of error, how much you accumulate error over time, like how this integral changes, and based on that, it would adjust the input to the plant. So that's the difference between proportional and the integral controller. Okay, so Ki actually looks at the integral of E dt, right? You see, like if you take 1 over S in the S domain, it's the same as taking the integral of this input. And well, can you guess what the derivative controller does? So the derivative controller basically calculates the derivative of error, right? dE over dt, right? So like how this error, let's say like the error first was like this much, it's now decreasing, but it gets like negative and it changes this much. So it takes the rate of change of the error, right? How error is changing, and based on that, it would adjust the input. In many cases, you want to have a combination of these. You want to look at the absolute value of the error, as well as, let's say, the integral of error, as well as the rate of change of error. You want to put all of them into one package and have a PID controller. Each one of them would take care of something, like one thing. One of them